Brian Vikings. It's 2024, and I'm going to update this energy overview unit. So here it goes. We're going to talk about thermochemistry, which is talking about potential energy and chemical bond energy. All right, so very quickly, the first law of thermodynamics is energy cannot be created or destroyed. We'll need to know the difference between potential energy and kinetic energy. Potential energy is the stuff locked inside the chemical bond, and then kinetic energy is measured with temperature. That's the motion of the particles. So thermochemistry is a transfer of energy from here to here. Now, note the energy didn't go away or wasn't destroyed. It was just transferred from one form into another. So we're going to look at different forms of energy. There's the chemical energy, stored mechanical energy, nuclear energy. There's thermal, electrical, and mechanical as well. But basically, we're going from potential to kinetic. Mostly, we're looking at chemical energy here. So, lots of examples of chemical energy where you burn something or you are getting some charge out. But thermal energy is really what you think of when you think of heat or when you think of something being hot, right? So there's the type of heat. There are three types of thermal energy: convection, conduction, and radiation. Okay, so with heat and temperature, they are not exactly the same thing. A sparkler will emit particles of metal that have temperatures up to 3,000 degrees Celsius, but they don't hurt you when they land on you because they have a high temperature but a low amount of energy. Why does that happen? Well, temperature is a measurement of the average kinetic energy, and it's measured in Celsius or Kelvin. Now, heat is talked about with the letter Q. We've talked about this before. It is the sum of the kinetic energies of the particles. And so it's a transfer of energy between two things. And we always go, and it's measured in joules. So heat is always measured from a high temperature to a low temperature. It's the movement of energy from one spot to another. So temperature is like how fast the particles are moving, and it's a literal definition of how fast the particles are. But heat is a form of energy transfer. So they're not the same thing. So quickly to kind of go through this, which has a greater temperature? 1,000 grams of water, 25 degrees Celsius, or 1,000 grams of water, 45 degrees Celsius. Well, that one obviously has a greater temperature because the Celsius is higher. Now, which one has a greater heat content? They're at the same temperature, but which one has more heat? And that would be this one because it has more mass. So you notice the heat is dependent on mass. Which sample has molecules with the greatest average kinetic energy? If average kinetic energy is temperature, so that would be this one. This one has the highest temperature, so it's the highest kinetic energy. And now, which one has the greatest total energy? Okay, and then that would be this one. All right, because remember, total energy is the sum of the energies. So you adding all the energies together. All right, we're going to clearly talk about the system and the surroundings. We need to understand, we'll be referring back to this a little bit later, but a system and the surroundings is just a perspective that we use to understand whether the heat is going in or out. So for a system, that is generally our chemical reaction. So if our chemical reaction happens in a beaker, everything inside of that beaker is the system. So the beaker and everything outside of the beaker is called the surroundings. Okay, so remember that beaker is not actually participating in a chemical reaction. It's the stuff inside the beaker. So it's a perspective that we try to use off of that. Okay, so let's briefly talk about an exothermic and an endothermic reaction. An exothermic reaction is something that releases heat. The energy flows from the system to the surroundings. The products will have a lower potential energy than the reactants, and the products will be more stable. Now, when we can easily see these in a thermochemical equation if the heat term is on the right side, or if we have the enthalpy out on the right. If the enthalpy is negative, it is an exothermic reaction. So either one is valid, and you will see both. So an exothermic reaction profile is shown like this, where we have the reactants and the products. Now the reactants are above the products, so the reactants have more energy. The energy has been given off by the reactants off to the surroundings, and what we have left over has less energy. And so this is an exothermic reaction. Now the products are actually more stable because they have less energy. All right, an endothermic reaction is the exact opposite, where where heat flows from the surroundings to the system. The products will have a higher potential energy, and the products will be less stable. And the energy heat term will be on the left side of the equation since it's going into the system, and it will be a positive delta H. You'll see why it's positive in a second. So notice how you get an increase in energy, you get an increase in enthalpy, so that's why it's endothermic. You get a positive change in enthalpy. So the reactants have less energy. They have now gained energy and become the products. All right, good to go. So we're going to quickly take our notes. And remember that the overview we're just really looking for is how we are turning chemical energy, and we are going to change it into kinetic energy. That is mostly what we're looking for. There's other variations that we can do, but that's mostly what we're looking for. Now, that is chemical energy is sometimes called enthalpy. Enthalpy. I'll give you a description in a second, and then the units for this are going to be kilojoules per mole. Now, kinetic energy is your temperature. That's the motion of the molecules. And the units for this are going to be degrees Celsius, or they're going to be Kelvin. Now, if I draw a simple methane molecule right here, it has 4 chemical bonds. Each one of those carbon to hydrogen bonds right here is potential energy. I want you to think of those chemical bonds as almost like a rubber band, that's ready to be broken, right? However, whenever it's broken, it actually requires energy, and we'll get to that in a second. It requires energy to break those bonds. So potential energy is locked in there, all right? And so that potential energy is enthalpy. This is enthalpy. That's potential energy. And an enthalpy has goes by the abbreviation or the letter H. So enthalpy H. That's better. Okay, doke. Now we talked about the system and the surroundings, right? So I'm briefly gonna just draw that. If we have a system, and then we have our surroundings. So if heat goes from the system to the surroundings, this is exothermic. So it's going to get hot. It's going to feel hot. Just pretend my surroundings are my hand and the system is the chemical reaction, like some fire, right? The heat goes from the fire into my hand, and so that's why it feels hot. This one is So if we go from the surroundings to the system, then it's going to be endothermic. And then that will feel cold. That's because it's taking the heat from my hand and pulling the heat out of my hand into the system. So pulling the heat out is going to make my skin feel cold. All right? So we will get a positive change in temperature here, and we will get a negative change in temperature here. Now, the change in temperature is going to be a little bit different later on. So kind of keep your wits about you when it comes to temperature and enthalpy. I'll point it out whenever we get there. So we're going to look at an exothermic reaction. And we're going to look at an endothermic reaction. Okay? So exothermic reactions are where you are forming bonds. Okay, you're forming chemical bonds. Forming. And for an endothermic, you are going to be breaking bonds. So it requires energy to like break a pencil, right? So it is an endothermic reaction is something where it requires energy. So breaking a bond is actually endothermic. Forming a bond is exothermic. Now, I will get a negative change in enthalpy. So that is my delta H. And for an exothermic reaction, and the heat term is on the right side. Let me see if I can, and then for an endothermic reaction, we will get a positive change in enthalpy, and the heat term is on the left side of the equation. I'll show you, see if I can get an example of that. All right, so I'm going to draw an energy profile here. I'm going to draw two of them. One for endothermic and one for exothermic. Now before I move on, now remember that the exothermic reaction had a negative delta H, but an exothermic reaction will also have a positive change in temperature. So I want you to like make sure you're really thinking about like, is the heat coming out? Is this gonna feel hot? Is this something going on? So you really have to be paying attention to your signs here. Okie doke. So on the y-axis, we're going to have energy. And on the x-axis, you can just get like the reaction progress. We'll do the same over here. Now, for an exothermic reaction, we will have our reactants here. And then we'll have our products here. I do not need to connect them, but to show an actual profile, I just need to show that the products have less energy. So you'll see that they have less energy. And they are more stable. More stable because they have less energy. You'll notice that over here, it's going to be the exact opposite. We're going to have the reactants. We're going to have the products. So now they will have more, the products will have more energy over here because they're higher on the list, right? And so they will be less stable. All right. Okie doke. Now, I'm going to put these two reactions up here. We kind of briefly went by them. They are I'm going to put two reactions where we have two CH18 All right. So what I did is I put in this chemical reaction that was already on the PowerPoint. I kind of goofed right here. This is supposed to be a plus sign. Now I'm kind of running out of room for the endothermic reaction. If you do have room for that, I recommend you go ahead and put in the endothermic reaction that's right here on your notes, and notice how the heat term is on the left side. All right, that's going to be it for me. I hope you have a good day.